Okay, now for something completely different, we're going to talk about mass spectrometry. Mass spectrometry is a technique which separates substances based on masses and polarities. There are two main aspects of mass spectrometry. First of all, the machine that you use for the technique, which is called a mass spectrometer. This is a schematic diagram of the machine. Before you ask, we do not have this machine at our school. Normally costs around $1 million per machine. So yeah, anyway. And the second thing is the result of the analysis, and this is shown in a mass spectrum, which is this. So I'm going to explain the principles of the mass spectrometer as well as how to read a mass spectrum. The reason why I bring up mass spectrometry, and it is such a fantastic technique, it has so many different applications, but in this particular context, this is a technique that allows you to determine the number of isotopes in an element, as well as the relative isotopic mass and the percentage abundance of each isotope. It's such a good technique. This is, I think, the best analytical technique that you're going to learn in BCE. I don't think you're going to like it as much as some of the other techniques later, but it is my favorite. And one of the reasons why I really like this technique is because it is such an old technique and we still manage to find new ways to use it. So the very first Nobel Prize that was won for this technique was in 1906, and Thomson was actually the physicist who discovered neutrons. And then up until 2002, people still found a new way to use the principle of mass spectrometry and to improve this technique. And interestingly, it has been used originally in physics and then in chemistry, and now it is used mainly in biochemistry and medicine. So this is one of the very first mass spectrometer that was built, very, very big, and they used it in an oil refinery company. So you can actually analyze the different composition of crude oil using this technique. And then it got a lot more compact. Actually, you don't know what this is for. This is when you have things like gas chromatography, which we'll talk about next term, maybe term 4. Modern MS instrumentation, so MS is mass spectrometry, of course. Um, you know the machine that you if you go to an airport, nobody goes to airports these days anymore, but you ever go to an airport and then you get selected and randomly swiped to test for any trace of drug, and then they put whatever sample that they collected from your luggage or your clothes into a machine. That is also a mass spectrometer. So it is used a lot these days for detection of illicit drugs. It's also used to detect, say, doping samples, trace of doping in urine or blood. You can use it for ethanol, but we normally don't. And this is the future. This hasn't. I think they started using this, but it's not very popular and widespread yet. And this is called the eye knife. So essentially, this is a real-time technique using mass spectrometer to, so when somebody is in a surgery and you want to remove a tumor, it actually could allow you to very quickly detect whether tissue is a healthy tissue or tumor tissue using mass spectrometry. So it is such a fantastic technique, and people still continue finding new ways to use it, which is why it's very important to know the fundamentals of how it works, which is what I'm going to tell you after I finish hyping up about the technique. I just love this technique so much. Anyway, this is an example of the machine. If you are going to become a scientist in the future, I don't think you necessarily have to know how to operate this machine. Like, you need to be specifically trained to be able to use the machine. Most of the time in major universities or research facilities, you can prepare your sample and then you give it to the technicians who are trained in operating this machine, and then they will return to you with the result. So you just really need to know to read the result, which is a graph. But I'll show you how the technique works anyway. So you start with this area, which is this is where the ionization starts. So we start here, and then you have, oh, that's an unfortunate color. Okay, so you start here with ionization, and then we're gonna go to acceleration, which is somewhere here. Actually, acceleration is 1, and then that's 2. So this is 1, this is 2. The signature of this mass spectrometer is the curve. So you're gonna see a curve here, and that's the most important step, which is the deflection. So you're gonna see the deflection here. You have a magnetic field in here. and then there's detection somewhere around this end. Okay, so there are 4 steps: ionization, acceleration, deflection, and detection. I'm going to give you an example of how this works. If we were to learn this in class, this is where I would do my magnets animation, but that's a shame. Okay, so you really want to get a big piece of paper and maybe do this diagram. So I'm going to go through each step, but this is the whole diagram. So you have ionization around here, there's a heating element, and then the electron beam. There is an electron trap here, and then acceleration, you have an electric field, deflection, and then detection. But I'm going to zoom in into each section. So you may want to watch the video and then go back and think about what you want to write down or annotate. Okay, so this is step 1. Let's say this is your input. So you start with a sample of boron. Remember that the whole point of this technique in this particular context is to determine how many isotopes an element has, the relative isotopic mass, as well as the percentage abundance of each isotope. So let's say we have 10 atoms of boron coming in. The first thing that happens normally before you actually get to ionization is you want to turn these atoms into gas. So there is a heating element represented by the sun. I don't think it's actually the sun, but there is a heating element. And in this particular case, for example, if you have solid boron, it's going to be converted to gas. And the main reason for this is just to improve the sensitivity of the technique and to speed it up. If something's a gas, it can go through the whole machine a lot more quickly than if it is solid or liquid. So let's say after you heat it up, it's gonna turn into gas. So they are a little bit further apart from each other. You have weak dispersion forces between them, and then you actually get to the first step, which is ionization. So ionization is, so as the sample passes into the ionization chamber, so you have an electric beam here, has been compared to a lightsaber by some of my students in the past. You can think of it that way. It is a beam of high energy or electricity, and what it is going to do is the electric beam, this energy, it's going to excite the valence electrons in these atoms to the point that one of the valence electron is going to leave the atom. So ionization will occur in the sense that the atom turns into an ion because one electron has been kicked out of it. So that's ionization. You supply the sample with high energy electricity to the point that you remove an electron from each atom of the sample. So after the electric beam has been shoot into the sample, you're going to end up with this. So notice the before and after. So each of these, assume that they are electrons. So every atom now turns into a positively charged ion, and then you have, if you have in this case 10 atoms, they will turn into 10 ions and 10 electrons in the machine. Now before the next step actually happens, there has to be an electron trap here to remove all of the electrons. So all the electrons will be removed, so you end up with just positively charged cations or ions. I mean, cations already mean positively charged. So you end up with cations in the machine. Okay, so all the thing that happened just then is just so that you convert from 10 atoms of boron to 10 positively charged boron ions. Now, once you get to here, we're going to go to step 2, which is acceleration. And acceleration is when you subject this 10 ions to an electric field, and that is going to just make them move really fast. I couldn't think of anything. Oh, this is good. I'm going to do this again. They're just going to move really fast, and they're going to move in a path. So this is just, again, to speed up the process, and they're going to move very, very quickly after the acceleration step. So not much happens. You just speed up their movement. This is the main event, step 3, deflection. So they're going to move very fast, and then they're going to go all the way down. But as they go down, they're going to be subjected to a magnetic field. And this is step 3, which is deflection. So they move very, very fast while being subjected to a magnetic field. And that is going to cause a separation based on mass. So all of these ions are positively charged, which means that they all will be attracted to the negative terminal of the magnetic field. However, the lighter ion would be able to deflect more towards the negative terminal compared to the heavier atom ions. Well, same. So if you go from here to here, you can see that so they all gonna go to the end, but they're not gonna go in one line or in the same speed, or if you will, the same deflection anymore. They're going to deflect depending on the size or the mass. So this is how the separation based on mass is achieved. And this is why you have to turn all of them into positively charged ions in the first place, because without that, they're not going to be attracted to the negative terminal of the power supply, magnetic field. So they all are attracted to the negative terminal of the magnetic field, but they will deflect at different degree based on how heavy or light they are. So that's deflection. And then in the end, they're going to be detected using a detector. Now, this detector itself is a whole machine that I'm not going to go into. I think we'll talk about some of it maybe next semester, but there's a detection. That's all you need to know for the time being. Now, once you have a detector, the result is going to be represented in this graph called the mass spectrum. And the amount of each ion, it's going to be represented in the vertical line. So in this case, you have 2 to 8. So there are 2 of the boron 10 ions compared to 8 of the boron 11 ion. And the actual mass is reflected on the horizontal line. And the fact that you have 2 lines also means that you have 2 isotopes. Let's talk about this in a little bit more detail. So the number of peaks is the mass spectrum. It's just a graph. So the number of peaks will tell you the number of isotopes. If you have 2 peaks, there are 2 isotopes. The horizontal axis, now it's actually mass per charge. So it's not necessarily the mass, but if the charge is 1 plus, mass per charge is just mass. There is a case when charge is 2 plus, but I don't think it ever comes up in VC. And the vertical axis is going to be the relative abundance of the peak, so the height of the peaks, if you will. So in this case, you know that 2 of these is boron 10 and 8 is boron 11, or a ratio of 1 to 4. So 20% is boron 10 and 80% is boron 11. So that gives you an indication of the percentage abundance of each isotope in the sample. All right, so based on that graph, the one thing that you are going to have to do as example 6 is I can give you this graph and ask you to calculate the relative atomic mass again. So you just need, no, this is not chlorine anymore, this is boron. You just need to be able to translate from the graph to relative isotopic mass as well as percentage abundance. So boron 10, it's going to have a relative isotopic mass. We're just going to use the horizontal axis of 10.01, and the height is 1, which is 20%. So that's going to be the percentage abundance of 20%. Boron 11 has a relative isotopic mass of 11.01 and a percentage abundance of 80%. So 80%. And then from here, you can calculate the relative atomic mass, which is going to be 10.01 times 20 plus 11.01 times 80 divided by 100. And then we should get an answer. So 10.01 times 20 plus 11.01 times 80 divided by 100. So 10.81 is going to be the relative atomic mass of boron using this mass spectrum. The last example, which is 7. So I give you a relative atomic mass, sorry, the mass spectrum here, but I also give you the height of the peak, and then let's read the question. You need to use this to calculate the percentage abundance. And you just need to convert this into a percentage, basically. So if I add all them all together, the total is 10 centimeter. And then you just need to convert 7.9 over 10 into a percentage. So the 24 magnesium is going to have a percentage abundance of 7.9 over 10, which is 79%. And then 25 magnesium is 1.0 over 10, which is 10%. And 26 magnesium is 1.1 over 10, which is 11%. So that is going to be the percentage abundance of these. That's it. Thank you.